Yeah, welcome to the class. Okay, let us start again. Okay, so last time we began looking at stochastic dynamics in mean field models. Okay, and one context we looked at was stochastic population dynamics. And we looked at how one can introduce stochasticity in an ad hoc way, right? And that is done usually in two ways. One, if you think of environmental stochasticity, we just merely add noise in an additive fashion. For example, if the mean field model was n dot is equal to f of n, we just add a term eta t, where eta t is a Gaussian white noise. What do we mean by that? We mean that eta t, the distribution is Gaussian, and the mean is 0, and it has no correlations. If I take any two arbitrary time points, they are uncorrelated. Okay, and the strength of the noise is sigma, which is basically variance. Sigma is standard deviation, and sigma square will be variance. Then we also had something like parametric stochasticity, and when we have parametric stochasticity, this leads to additive noise, whereas parametric stochasticity leads to multiplicative noise. We haven't discussed this well as of now. So the general form of this will look like this, where eta t follows the same definition, with the main change being that the coefficient of eta t is not a constant. It is now a state dependent function. Okay, that's why we call it multiplicative noise. The noise multiplies with the state variable, and whenever we have such a multiplicative noise, okay, we need to define the calculus we are going to use. So I will explain this maybe next week. What exactly do we mean by that, and why am I writing this? I will explain that maybe in the next class. Okay, and then what we then went on to do was, let's consider dynamics near equilibrium, near stable equilibrium, to be very precise. Okay, we know that if you are at an unstable equilibrium and if you make any perturbation, the system just flows away, right? So therefore we said, let's look at system near equilibrium. What happens to the role of stochasticity when the system is near equilibrium? So how does stochasticity affect the dynamics near equilibrium? In the deterministic model, if we had just this, right? Okay, and then if x is the deviation from equilibrium, if x was the current value minus deviation from equilibrium, where x is very, very small, then we know that x dot follows the simple equation where alpha is equal to modulus of this. Okay, and then we know that basically this perturbation decays with time. This leads to a simple exponential decay, right? We already know this, so let's just recall what we know from mean field analysis. And what's the interpretation of alpha? Alpha was return rate to the equilibrium. Okay, and tau which is 1 over alpha, if I were to define 1 over alpha as a time scale, would be the time to return to equilibrium. Okay, what this means is that when alpha is large, the time to return will be very small. When alpha is small, the time to return will be very large. This is something we already know from the mean field system. So now the question is, what's the role of stochasticity? Role of noise. Okay. And then going back to the population model, the model will now look like this: the additive noise model, where it is as defined before, a Gaussian white noise. Okay, and then we have again to the same Taylor series analysis, and what we then find is that we have x dot now follows minus alpha x plus eta of t. So the noise term doesn't change, but basically the perturbation which was acting on the entire population now basically merely acts on the perturbation itself. The same noise structure hasn't changed at all. Okay. Okay, so now of course when we do this, the assumption is that x is small, and for this equation to hold true, x must continue to be small, which means the strength of noise is sufficiently small that the linear approximation holds true. Okay, so that's when we can use sigma sufficiently small that linear approximation around holds true. Okay, this is just recapping what we have done so far. Any questions before I go forward? Okay, no questions, I'll go forward. So we now have this. Where alpha is greater than 0 and eta t is Gaussian white noise. Okay, this also has a very this system has been very naturally studied very extensively in the literature. It's called Ornstein-Uhlenbeck process. It's a very, very important stochastic process, as you can imagine, right? What this is really studying is what's the role of stochasticity around a stable equilibrium, right? So it's a very, very well-studied process. In a general way, it's also called Langevin equation. Of course, Langevin equation is a much more general name. Langevin equation could also be non-linear. Okay, so it's basically linear Langevin equation. Okay, Langevin equation is any equation which has the form x dot is equal to f of x plus g of x eta t, and it could even have more terms. As long as there is some noise term, we call them Langevin equation. So now it's again a stochastic process. As you can see, x varies with time, of course, and if x varies with time stochastically, therefore this is a stochastic process. And then when we are interested in any stochastic process, as I told you, as a sort of rule of thumb, we want to calculate all the moments, but for the purpose of this class, we often focus on mean, variance, covariance or correlation, and finally how the probability density evolves with time. So these are the key quantities we are often interested in any stochastic process, and let us see how we can calculate this. Okay. Now for this process, there are many methods to do so. I will just adopt one simple method. Okay. So so for this, you may have heard of a method called okay, I myself forgot the method name. Okay, so there is a this when you do this, one of your first courses in differential equations, you learn some methods. Suddenly the name is slipping my mind. Okay, so we know that when there's an equation of this form, where you know the solution for one part very well, and the other part is an additive term. Okay, there are some substitutions that work. Okay, and in this case, it is this type of substitution. Okay, this is motivated by the fact that if we did not have the noise term, we know that the solution is an exponential in time. X varies exponentially with time. That's the main motivation for choosing a form of this type. So basically, I am now transforming the variable from x to y, where y is given by x times e power alpha t. Okay, so let's see how this substitution helps. This is just a substitution. So if we do this now, we can calculate y dot. What is going to be y dot? So when you take the derivative on the right hand side with two terms, both of which depend on time, you just have to take turns for each of them, right? So first will be derivative of this, and keeping this as a constant. So we have e power alpha t, that's kept constant, and the derivative of x. Okay, and then the second term will be keep x as a constant and take the derivative of the second term, and the derivative of e power alpha t is alpha times e power alpha t. Okay, so now y dot follows this equation, but now in this we have x dot on the right hand side, and we do already know there is an expression for x dot. So what is that? That is equal to e power alpha t. I'm not basically now going to expand, substitute x dot with the right hand side of this equation. Okay, so the first term now therefore becomes, let me just do it in two steps, alpha x plus eta t plus x alpha e power alpha t. Let us continue our expansion. So first term will be minus alpha x e power alpha t. The second term will be e power alpha t eta t plus x alpha e power alpha t. Okay, so you can now see that the first and the third term are basically same. They cancel out. So basically this substitution trick follows from the fact that you actually get such a cancellation. So we now have a simplified equation for y dot, which is e power alpha t eta t. Is everyone with me so far? So now what is good about this equation is the left hand side depends on y, right hand side depends only on x, only on time. So we can just do a simple integration now. So let's do the integration on both the sides from 0 to t. So what we will have is basically 0 to t y dot, okay, dt. Let's not call it dt, let's call it maybe ds is equal to alpha s. So the dummy variable, I'm calling that s instead of t, 0 to t. Okay, so the left hand side basically becomes y of t minus y of 0, whereas the right hand side becomes integral. It just remains as it is. We don't know what is this integration, huh? But effectively what you can interpret the right hand side as follows: eta s is the stochastic term, right? And s is varying from 0 to t. Okay, the start of your stochastic process up to some arbitrary time t, and you multiply eta of s with e power alpha s, and then you take the integral. Okay. Now let's go back to this. Now, eventually we want to go back to x. So because that's what we understand, right? X is the perturbation from equilibrium. How do I go from x to y? You know, this implies that x is basically y e power minus alpha t, right? So if I have y, and if you multiply y by e power minus alpha t, we get x. So what we now do is multiply the entire equation with e power minus alpha t. So then what we have is yt e power minus alpha t. I'll take the y0 on the right hand side. So y0 e power minus alpha t, okay, plus 0 to t e power minus alpha t plus alpha s, this. Is it fine, everyone? Okay, so what is this term? This is nothing but x of t. So as I told you, yt times e power minus alpha t is just nothing but xt. That just follows from the definition or substitution itself. Okay. What is y of 0? Y of 0. So if you say, if you, in this equation, if you set x of 0, that will be y of 0 e power minus 0. That is basically y of 0. So what this tells you is that x of 0 is nothing but y of 0. So I can just replace y0 with x0. And e power minus alpha t remains as it is. Yeah, and then we have 0 to t e power minus alpha t minus s. Okay. Okay, sorry for a bad box, but that missed a few things. I'll try to see if I can redo it. Okay, so this is basically how the stochastic process is changing. If you know x of 0, some initial condition that you chose, the effect of that, what does this really tell us, right? You know, this is, you know, this shows that the effect of initial condition is given by this. And what is that? It is decaying exponentially. So the initial amplitude, initial perturbation amplitude decays exponentially, right? That's what the first term is telling. However, there is an additional term, which is the effect of stochasticity. Okay, and that is non-zero, right? So therefore, even if you wait really long, it doesn't mean that, although this term actually does become zero, it doesn't mean this term is zero. Okay, and this really helps us quantify what is xt after a while. Okay, this is an exact solution, by the way. Okay, when I say, you know, it sounds like a bit of a crazy thing to say, an exact solution for a stochastic process. Okay, it takes some time to understand. Just as the rate of change has an equation given by this, a stochastic process, the solution is also a stochastic process. Okay, and this is an exact solution, analytically exact solution of the OU process. Okay, any questions? Any further questions? There are other forms which actually do equally well, by the way. I don't know if I will have time to cover those, or the methods to cover those. Okay, so now let us understand this. Okay, we have instead of a rate equation, we now have a a proper just an expression for the stochastic process. So from that, can we calculate mean, variance, and all these things? Let us see. Okay. Any questions so far? Was the algebra okay? Okay, so I'm assuming that's okay. So now let's move forward. Let's calculate the mean. Before we even compute the mean, let's take some limiting case. It's always useful to, whenever you have any new system, new equation, okay, just always think of, can I think of some limiting cases? What's a limiting case for which you already know the answer? Is there a limiting case of this for which you understand well?
When there is no noise term.
So when there is no noise term, obviously. So when this term is 0, what happens to the final equation? In this equation, as you can see, eta is 0, meaning no noise, right? What happens to this term? The second term? Second term basically becomes 0, right? So that means that you now have xt is equal to x of 0 e power minus alpha t. Does it make sense? It does, right? It's basically the simple equation for how the perturbation dies, and that is indeed the solution. Okay. So for this limiting case works well. Is there any other limiting case you know? That's one limiting case. What are the limiting cases do you know? Any guess? So when you have two terms, how do you obtain limiting cases? One is you drop one of them, right? You got one limiting case by dropping one of them. That's a hint.
So can we drop the initial part of it? No.
What do you mean by
First term? Alpha.
First term? Okay, exactly. So what does the dropping the first term mean? No, let's say alpha is equal to 0. What does that mean?
We are at equilibrium.
No. At equilibrium is x equal to 0.
We are at the critical point that we.
Okay, that's the dynamical systems way of thinking. That's correct. You're at the critical point. It's like the bifurcation point. You're absolutely right. But that's correct. So what does this equation mean though? Forget that part of the dynamical system, population dynamics part and critical point. What does this equation mean? So let's write that in a discrete form. Maybe that might, so this is dx by dt, right? Okay, let's write this in the following way. Dx is equal to eta of t dt. Okay. Okay, does that make any sense? So what is this? This is the incrementing or changes in. This is the change in value of x, right? And this is the rate of change, which is stochastic term, times dt.
Increment can be positive or negative.
Yeah, this can be positive or negative. And I told you that a differential equation of this type is also written in the following equivalent way, right? Tx is equal to, I don't know if I probably did not spend much time. So maybe let's just do it again, once again, just to remind you. Remember, if we have a general equation of this type, this is the physicist's way of writing, but mathematicians prefer an alternative way, which is this. They don't write eta t, they instead write dw of t. Okay. And then, so alpha equal to 0 in our case. corresponds to fx equal to 0. So basically you have dx is equal to dw of t. And do you remember what was dw? It had various properties, right? So, and you remember the interpretation of that? So w itself basically represented Brownian motion, right? What this now means is that the increment in x, the state variable, is also same as the increments in Brownian motion. Therefore, x itself now becomes Brownian motion. Okay, is that clear to everyone? So basically, alpha is equal to 0 takes you to the case of Brownian motion. Okay, now the state variable just follows a Brownian motion. That's another limit. Okay, now if you have that limit in this equation, this term basically remains x0 because this becomes 1, and then alpha is equal to 0 means this term just goes away, and then basically what you have is integral of eta over a small, whatever the interval that you are thinking of. Okay, so again, this is a, this is consistent with the idea of Brownian motion, that basically if you take lots of random steps given by eta s, if you integrate all of it, of course this one will be not there when alpha is equal to 0, right? You get the final location. Okay, that's the basic idea. So the two limits, eta equal to 0, while that takes you to the deterministic mean field model, alpha is equal to 0 basically takes you to the Brownian motion limit. And this Brownian motion is now the state variable, x need not be the location. Okay, so it's always useful to think of these limiting cases. Okay, okay, now having done that, now let's go back and think and calculate the quantities of our interest. Oh, okay, so OU process solution is what we have, right? Which is x of t is x0 e power minus alpha t plus integral of e power minus okay, this is what we have. Okay, I hope I didn't miss any term. Okay, that looks good. So let's now find out the mean value of the state variable, xt. So let us apply this average to the entire equation. So average of the left hand side is average of this entire equation, and it's a summation. Average of summations is summations of averages, right? So basically that means we can just apply summations independently to both the terms. Is that fine? And if x0 is a given value, an initial perturbation, that means this entire term is deterministic. So the average is basically same as the term itself. And that doesn't really change. So the first term remains as it is. What about the second term? So we have an average of an integral. Okay, now of course, so to really do this calculation in a mathematically rigorous way, you need to really probably prove some theorems.
Is this average over time?
That's a very good point. Are you talking about average over time? What do we mean by an average? Okay, it's a great question. So in all of these cases, when we say, so just think, we want to know what is the average of xt, right? Meaning I want a time dependent average. That's what I'm interested in, right? If x0 is the current location, if I wait t units of time or t continuous time units, okay, what is the value of that xt and what is the average of that xt? So I'm preserving t here. So the average here means that there are many stochastic paths that are possible from 0 to t, and that means there are many values of xt possible. The average here is average over all possible values that xt can take at time t. Okay,
So this is similar to like ensemble average?
this is an ensemble average.
Okay, okay.
So it's an ensemble average of x of t at not t. Okay, I mean x of t is x of t means at t, but I'm just making it explicit. Okay. So if you were, if you were to think, if you want to think it in a very numerical way, if you were to simulate the OU process with some initial condition x0, okay, you want, now you will run this one time, you will get some value of xt, you will get another time, another value of xt, you run this million times, and what's the average of all those million xt values? That's what we are doing. Okay, so that's the first term. Now what about this one? So this is a deterministic term, e power minus alpha t minus s, right? And this is the only stochastic term. That means that this average can be taken inside. So we have 0t e power minus alpha. Okay, is it fine? And we do know what is eta s average, right? What was that? That was 0. So therefore, this term is 0. And what you basically have is that the average of xt is given by the initial value you chose times e power minus alpha t. Is that clear to everyone? It means the average value itself decays exponentially with time. Okay. And if you now look at the asymptotic limit, if I wait long enough, asymptotic average, right? That would be limit of t goes to infinity of x of t. What will that be? It will be 0 because the exponential of minus alpha t itself goes to 0. Any questions on this? So that's our calculation of mean. So there's nothing very surprising here, right? So it makes intuitive sense to us. And again, take the limit alpha goes to 0. Does it make sense? If alpha goes to 0, x of t would be same as x of 0, right? Remember, x of alpha equal to 0 corresponds to Brownian motion, and we know that the mean value of the location at time t is same as the original location, right? So xt is equal to x0 again makes sense. Okay, excellent. Can we move forward now? So we now want to calculate variance, covariance, and correlation. But let me just tell you one simple thing. If you take covariance between two variables, x and y, and if you now set y is equal to x, what will this be? This is nothing but variance of the random variable x. Do all of you agree with this? Because covariance is equal to this, right? X minus x bar times y minus y bar. If I now set y is also equal to x, then what we have is, the right hand side here becomes x minus x bar whole square average, which is nothing but this. Okay. So So covariance, if I calculate covariance, and if we calculate covariance for the same variable, then we'll get the variance. Okay. Now another point to keep in mind, which I have told is, if I want covariance between two variables, then I can find covariance or a correlation between two variables. And then if we now divide by the sigma x, sigma y, I'll get correlation. So basically what these two tell me is that if I calculate covariance, I can get variance, I can also get correlation. So let's focus on calculating covariance for the old process. So specifically, this is the covariance we are interested in. Covariance between the value of x at time t. So the y for us actually is not a different process, but the same process, but at a different time. Okay. So x of t and x of t prime. What will this be? By definition, this will be x of t minus x bar of t, right, times x of t prime minus. So I'm using bar and angular brackets sort of interchangeably. So the xt bar here means that the average of xt. Okay. Whereas outside I'm using angular brackets. So again, they both mean the same thing, which is the ensemble average. So fine, the definition of covariance, but and as you do know, we already know xt, right? We know this x0 e power minus alpha t, and we also know therefore that xt prime is equal to x0 e power minus alpha t prime. We already know these expressions, the mean values. Let us, this x0 is a very arbitrary value anyway, right? So what we will do, let's assume that x of 0 is 0, primarily because it's just going to, actually it's going to make no difference whatsoever at our calculations. So let's just make the simple assumption. As I told you, it doesn't make any difference because the difference between xt and x bar t, if I now go back to this expression, right, xt and the average, this is x of t's expression is full expression, right, and the x bar is given by this expression. If I take the difference, the x0 anyway goes away. X0 doesn't really matter, so actually I don't need to even make the assumption. So if I take the difference, what I am left with is basically this integral term. Okay, so actually I don't need to make the assumption, it's actually not required. Okay, so now what we will do is just calculate this xt of x bar t is basically equal to integral 0 to t e power minus alpha. So this, let me just warn you, there is some amount of algebra now. I'll try my best to keep you all on track. So here I have every one of the terms as a prime. Is everyone fine so far with me? So let us try to intuitively think, what are we really trying to do with this covariance calculation? So as you know, we are interested in the stochastic process x changing over time. It's probably doing something like this, crazy like this. Okay, I mean, my graph doesn't probably look very nice. Something like this. So what we are trying to do is we have identified some time point t here, another time point t prime here. We're basically trying to ask, given that there was some x0 here at time, it doesn't have to be as a zero as we just found out. We began with some x0 and it's evolving over time. We have figured out that the average, the long-term average of this trajectory is basically 0. Okay, it's going around 0. How do we know that? We know that from this. So the average is x0 times e power minus sin t. So asymptotic average of this xt is basically 0. That means that xt is going back and forth equally likely. Okay, that's what we know. We still don't know exactly other details. So the next thing, so this is a possible trajectory. We are looking at 2 points t and t prime. We want to know how these two are related to one another. Okay, if these 2 points were unrelated, this covariance should be 0. If they're strongly related, they must be greater than 1. If they're anti-related, if they're opposite of what they were, they must also be a negative value. Okay. Okay, that's what we are trying to find out. Okay, so now we know that the difference of xt from x average is this, and the difference is this. Let's now plug this in the covariance expression. Will now basically become average of these two integrals. Hey, please do keep a watch on all the mistakes I'm going to make now. Is that fine? So I have just multiplied now both, this integral with this integral to get the covariance term. So now the angular brackets remain as they are. So now what I will try to do is I'll just pool together as many terms as possible. We can pool together these exponential terms. Okay, especially look at the terms that do not require the integration. So this depends on s, right? In the exponential, the minus alpha s depends, has to be integrated. Minus alpha s prime needs to be integrated. By this, minus alpha times minus t doesn't have to undergo integration at all. It's a constant. Likewise, minus alpha t prime doesn't have to go integration. So I can just take that out. Okay.
So that
what we
should
have
be
is
t
e
minus
power.
s.
What should be t minus s?
Minus alpha t minus s.
Oh, I just swapped. See, look. Okay, I'll just make it plus here now. Is that fine? That's same, no? Is that
Yes.
fine? Okay. Sorry. Thanks for catching that. So alpha s and alpha s prime will have to undergo integration, but not the t and t prime. So we have minus alpha t plus t prime that actually just comes out of the integration, and then we have these terms e power alpha s plus s prime eta s prime ds prime. Is that fine? Okay. Now we have this is a constant, and this can be taken out of the angular bracket. I hope everyone agrees. Now, how much can these two brackets come inside? Okay, they can come inside as long as there are only stochastic terms left, right? So is the exponential alpha s plus s prime a stochastic term? No, right? They are all just parameters of either the model or the integrants. So this term can come inside here. It can come inside the integral here. It can come even beyond this. Can it go further inside? No, because this is a stochastic variable. So this space, by the way, I've very conveniently forgotten another integral. There are two integrals, right? So one goes from 0 to t, and that goes from 0 to t prime. Okay. E power alpha s plus s prime and again this from this side, this is just integral, the infinitesimals of the integration, they are not stochastic variables. So this is the the simplified expression now. Of course, the only thing we have done is we have taken the angular brackets deep inside as much as we could. Okay, so is this term 0? What is this term? So let's go back to the first page where we wrote this. This is basically sigma squared times the Dirac delta function. What this means is that when t is not equal to t prime, this is 0. But when t is equal to t prime, it's basically highly correlated. It's actually a delta function. Okay, so we can replace this by sigma squared delta s minus s prime. Okay, now I totally understand that some of you have never used Dirac delta functions and who has never really, again, sigma square is a constant, so I can take this out all the way. These steps will be totally difficult to understand, so don't worry, it's totally fine. We will in the end interpret what these mean.
So the integral limits should be 0 to t and t dash.
Oh yeah, thank you. So very happy to know that people are keeping track of all my mistakes. Okay, great. So far fine, everyone. So use this simplification. Okay, basically I have just used the property of this random variable eta t, eta s or eta t, that when you multiply them and take the average, it's basically a Dirac delta function. Okay, and now this is the integral we have to do, and so we know that we have now gotten rid of the stochastic variable, and we now have, this is basically now a deterministic integral. Okay, with the Dirac delta function, and to do this integral, you need to know one rule. If you don't know, it's totally fine. I know I don't expect that you will be able to. So let me just use a different notation. So let's let's say this is S prime. So let's say this goes from something like this. So f of s is some function, and then you're multiplying with the Dirac delta function, and then you're integrating over the this variable s prime. Okay, so now we know the property of Dirac delta function. It's 0 everywhere except when s is equal to s prime, right? What this means is that I have taken a function. Let's say this function f has some. It has some properties like this, some features like this. So there's some value s prime here. Oh, okay. So there's some value s here. Okay, and it's varying as a function of s prime. So I'm multiplying with a function which is 0 everywhere. So here, I've multiplied with the function which is 0 everywhere. 0, 0, 0, 0, 0, everywhere it is 0. Only at some value it is not 0. Which basically means that I'm multiplying with a function which is 0 everywhere except s, at one specific value, and then I'm adding up all the values. So it intuitively makes sense that this integral will be basically the value of f only at this specific value of the s prime. Okay, so this is the result we will use from our understanding of Dirac delta functions. So how many of you knew this? How many of you remember this? How many of you have come across Dirac delta function? Let me ask you a more general question. You must be probably from physics background, otherwise you wouldn't have come across this. Bevan, so Paras, where did you are from an engineering background?
Yes.
So that, okay. So you have come across dark data functions.
Yes. Yes.
Okay. Dharanish, yes. Naveen, are you from physics too? Of course, Vivek.
Yes, sir.
You're from physics, okay. Ashrit, okay. So engineering people also do use dark delta functions. That's nice to know. Papitra, okay, not bad. So some of you have come across. So it's a very fascinating function. Okay. So if you have time, just look that up, how it's defined, its properties, and so on. Okay. So if you don't know, it's fine. One way to think about this, it's a function which is 0 everywhere but except at one value, and that one specific value is infinitely large. Okay, that's the way it's defined. It's a mathematically ill-defined function if you go and ask mathematicians, but it works for physicists. Okay, so we have gone through these integrations now. Okay, and so I'm going to use this result. And if I use this result, what this means is that I'm going to use one of the two integrals and get this done. So I'm going to use the S prime integral, this integral. And what this means is that the function here is the e power alpha s plus s prime is the function. And it is to be evaluated only at one value, which is s prime is equal to s. So it now becomes e power 2 alpha s ds. So basically, I have used this property of the Dirac delta function. And then finally, we are almost there. And this is a standard deterministic integration. Okay. That, what is that? Let's just do it. 0 to t e power 2 alpha s ds is equal to 1 over 2 alpha e power 2 alpha s from 0 to t, which is basically 1 over 2 alpha e power 2 alpha t minus 1. So this is a standard integration, and then you multiply it with this, which finally gives us to the formula for covariance. Now you must wake up. If
shouldn't there also be an alpha when you first integrate 1 by alpha? Like for S dash
integration,
the S dash integration.
no, I mean, so look at this now. This recall property of the Dirac delta function. So f of s is e power alpha s plus s prime. I'm not integrating over, so this property, if it's true, I don't need to get 1 over alpha, right?
Yes.
Okay. So you can think of it as, e power alpha s has come out because I'm integrating only s prime now. So what I have is e power alpha s prime times delta s minus s prime times ds prime. That's the integration I have done. And that will be e power alpha s. Okay.
Right. Okay.
Thank you for asking. Okay. So now, so please redo the calculations because, my writing is not the prettiest writing in the world. And I have also skipped 1 or 2 small steps. And then, so we have this was the prefactor, and this integration is basically this. So I'm going to take the 2 alpha here, and then I'm going to take e power 2 alpha t minus 1. Cool. So we now have an expression for the covariance. Okay. Let us take one step further and simplify it. So let me take t power 2 alpha t outside. And let me know if this is correct. E power minus. So I have taken Is this fine, everyone? Sorry. Oh, again, another sorry. This I really must find. Learn to write well. I think it has improved since last semester, but I still a long way to go. Okay. So this is the expression for covariance. Okay, let us now try to understand this. The first one, as I told you, we can get variance, which is x minus x bar whole square at time t, as a function of time, which is basically the mean square displacement. If you think about it, will be, what will that be? If we just set t is equal to t prime, right? Will be basically covariance of xt and xt. What is that going to be? So this term basically becomes, what does it become? It becomes 1 because t is equal to t prime plus sigma square by 2 alpha 1 minus e power minus 2 alpha t. So sigma square at time t for the OU process, the variance is given by this. So sigma square is the noise of the external variable, and you are dividing it by 2 alpha, where alpha is the return rate, and you multiply the entire thing with 1 minus e power minus 2 alpha t. Okay. So now let's again try to understand this a bit further. Let us look at the asymptotic limit. Which is t goes to infinity. What is, if you wait long enough, what happens to the variance? Then basically, as you can see, e power minus 2 alpha t terms goes to 0. So asymptotic limit will be sigma square by alpha. Okay. Now, what we can also do is we can actually plot this as a function of t. So we can plot sigma square t as a function of t. How will this look like? So the asymptotic limit is sigma square by 2 alpha, and then it is reaching there at 1 minus something like this. So what it means is that it actually probably reach something like this. So it's reaching a constant value. The variance of this process basically is a finite variance. If you wait long enough. So what does this variance mean, by the way? It's a variance from the equilibrium or of mean value, right? What was the mean value? Mean value itself was, asymptotic mean value was 0. So what is the asymptotic variance? Meaning, asymptotic mean value is 0. What's the variation around this asymptotic mean? That actually is a constant value, although it's a dynamic process. That's what this indicates. Okay. Which is not surprising, because why is it not surprising? If you go back to the original equation, there is a term that's pulling you back, right? So this term is pulling you back. Therefore, the variance just doesn't keep on adding up. So it actually has a limit of how far the system will go. The variance is limited because the x dot, there is a pulling term back to the equilibrium, which is x equal to 0. Okay, does that make sense? Okay, so now let's look at, again, always think of interesting limiting cases. One is asymptotic limit. What else can we look at? What are the other interesting limits to look at? Sigma is equal to 0 is a very trivial limit, right? Which means there is no noise, no stochasticity. So that we should probably check. We won't even look at that. What's the other interesting limit to look at? Come on, people.
T is equals to 0.
t is equal to 0 mean, wherever you began, what do you expect? So x0 is where you began. And then
Okay.
what is the variance around that? That will be, what do you expect it to be? It
Zero.
will be
So,
0, right? So if you set t
so
is
we are
equal to
saying
0,
that at 0 time point, there is no noise in the system.
no, 0 is where you began. The noise is just beginning to act.
Okay.
X0 is where you began, right?
Uh-huh.
So I mean, noise hasn't even acted, it's just beginning to act now. So the
Okay.
variance around X0 is a given point, deterministic given initial condition.
Uh-huh.
Okay, so there is no variance. Okay, we should think of all possible. I'm not. Please don't think I'm ridiculing what you said. I think it's also a useful thing to think. Okay, but one can also think of one can also think x0 as a stochastic variable. If I were to pick x0 stochastically, then how will I find? Then that would just become variance of x0 itself, whatever your input x0 was. Okay. Any other limit? That's
Large
interesting.
values of alpha.
Sorry.
Large values of alpha.
What does large value of alpha mean?
The pushing back force, like the force pushing back to the thing, is higher.
Very, very high. No. So what happens to the variance in that case? That's a useful thing. We can think of large alpha, large pull to equilibrium, right? So what do you expect in that case? Should the variance be large or high?
Small.
Must be small, right? And indeed, right, sigma square, right, is proportional to 1 over alpha. So it's consistent with our expectations. So larger the alpha, smaller the sigma t. So the system is pushing back very rapidly, pulling back very rapidly. That means that the variance will be low. Very good. That's great. What else?
Then another case would be when alpha is very small.
Exactly, right? Small alpha, right? Low pull to equilibrium. So what do you expect in that case? Noise will take you far away, right?
Yes.
Noise can take away from equilibrium. And therefore, what do you expect in such case? Large variance, right? And indeed, that's what you find, because again, sigma square is proportional to 1 over alpha. Sigma will be large. Excellent. Okay.
But in this case, because of we are having that large variance, so we first started with the assumption that
exactly
the noise would be in some limit, right?
So the noise sigma is still given, right? Sigma square was, you can say sigma is still fixed. Sigma I'm not increasing the noise, external environmental noise. What's happening is that alpha is becoming low, right?
Okay, yeah.
You can, but your argument could be still valid. When the pull is very weak, even the small sigma can take you away from the linear approximation limit. Okay, so anyway, that's an important point. This could mean that we might be deviating from the deterministic limit. Okay, what's the true limiting case here? I'm just waiting for someone to say. Alpha is equal to 0, right? We know that then x becomes a Brownian motion.
Then there is no returning back in that.
But we also know something about that. What's the mean square displacement?
T over there.
It's
yes.
proportional. Do we get that here? What happens if we set alpha to 0? It becomes infinity, but there's a catch. We were looking at the asymptotic limit. So we must go back to the full expression. Okay. the full expression, what we need to do is we actually go back to the full expression. 2 alpha 1 minus e power 2 alpha t. And we take the limit alpha goes to 0. Okay. Limit alpha goes to 0. What do we now find? To do that, what we basically do is expand this. It becomes 1 minus 2 alpha t plus 4 alpha square t square by 2 factorial and so on. Okay, is it fine? You remember, basically I used this e power x is 1 plus x squared by 2 factorial. I use this. Okay, so we have, so let's see, alpha goes to, oh, not infinity, 0. So now 1 cancels out, and the first term is 2 alpha t. Okay, so now go back to the limit. Limit alpha goes to 0, sigma squared by 2 alpha t plus 2 alpha square t square and so on. There are many terms, right? And then let us take alpha, these two will cancel to become alpha and so on. Now apply the limit. Okay, what do we get now? Now we get, if you apply now the limit alpha goes to 0, again I made a mistake here, 0, what do we get? So we have first term will be sigma square t, and second term will be, and second and higher order terms will be what? So this is 2 alpha remains, no, it becomes 0. So they're all 0. So is it expected? So what were we calculating by the way? We were calculating sigma t square, right? So this basically means that sigma t square is sigma square t when, which is exactly the mean square displacement for. So it works. Huh? So life is consistent. So now you should not think of x as an approximation of a nonlinear system. You must think of x as a variable that just follows the OU process exactly. Okay. So now, and then with that starting point, if you now set alpha is equal to 0, x now follows Brownian motion exactly. And indeed, the expression we derived for sigma t square continues to hold true even in that limit. Is everyone fine? Any questions on this?
Yeah, I have a question.
Yes, please.
So if we were looking at a dynamical system with a nonlinear response, close to the bifurcation point, we wouldn't be able to write this linearized equation, right?
Yeah, you're right. You will need to add some nonlinear terms. You're right. Or you have to keep the work still within the regime where the perturbations are really tiny. Yeah, but you're absolutely right. You do need to add nonlinear terms if it's a nonlinear system.
Okay, thanks.
Any other questions? Okay. Finally, so we have done a lot of things with variance. So let's now go back to correlation. So correlation between xt and xt prime is basically covariance between xt and xt prime divided by the sigma square, right? Okay, so let's go back. Now there is a bit of a small catch here. So as you can see, the covariance xt prime is given by, depends on both t and t prime, and sigma t depends on t, right? Okay, so now what we will do is, we won't bother with the exact expression. So you basically should multiply with sigma t times sigma t prime is what you should really be doing. Okay, now I'm going to do a bit of a shortcut here. I'm going to just divide the covariance by just sigma t square. Is that fine with everyone? I'm going to put a small amount of cheating here involved. But to make life little easy, I'm going to assume that t and t prime are not so far that I don't have to worry about the distinction between sigma t square and sigma t prime square. With that assumption, I'm going to just divide covariance by sigma t square. Okay, but you should just try it out entirely by yourself, or that results really don't change too much even if you were to account for that difference. If I now do that, covariance by sigma t square, if I divide this by this, these terms will go away, right? And these terms will also go away. And what you are left basically with is just this. Okay. Sigma x of t. So I've done, as I told you, I have done a small amount of mistake here. No. Okay. And let tau be the lag, t minus t prime, where and also which is greater than 0. So t is greater than t prime. What this basically tells is the correlation of the variables xt and xt prime, which is separated by a lag tau, is basically this. What does this mean? Correlation decays exponentially. Is it reasonable? Apart from the the small cheating I did, okay, which is why I have this squiggly equal here. Okay, so basically go back to this diagram, time series diagram I wrote. T and t prime. Okay, so the value of xt and xt prime, the relationship between them is basically decaying exponentially, and farther apart they are, the lower the relationship between them, lower the correlation between them. And in fact, the relationship between them is decaying exponentially, and in fact it is decaying exponentially with a characteristic time, right? So if 1 over alpha is the characteristic time of the system, characteristic decay time of correlations. What this means is that if the system has a return rate of alpha, it is at the same return rate, the correlations between the two data points are decaying. And this is a very, very useful result for the very simple reason, right? Why? You often have a time series, stochastic time series, okay? You don't know what is the Langevin equation. You don't know what is the parameter value alpha. So what you can do is you can calculate the, what we call autocorrelation. It's also called autocorrelation function because it's between the same variables x, right? So you calculate the autocorrelation function at different lags, and you fit an exponential, and that fit will give you a value of alpha. So even if you just knew how the stochastic variable is changing over time without knowing the equation, I can estimate the value of alpha which is in the equation. Okay, and therefore it's a very useful result. For systems which are near the equilibrium and where the linear approximation is valid, this is a great way to estimate the because it's because this calculation can be done with any given data set, right? So you can actually calculate alpha from a given data set. Okay.
Here, for calculating alpha, do we need to know that the type of noise that is adding in the system?
The assumption is it's a Gaussian white noise.
Okay.
Yeah, that's the assumption with which we have worked throughout, right?
Okay.
If that assumption is wrong, these calculations are also wrong.
Yes.
Okay. So I will stop now and I will give you a lab assignment. Okay. So now how do we put all of this to use? I have already given you some hint. We can put to use, for example, by calculating the autocorrelation function. So if somebody just gave you time series data, some state variable, some populations as a function of X, okay, as a function of time, we can calculate this autocorrelation function. Okay. And then from that, you can estimate the value of alpha. But what do I do with this? That's the question I'm going to ask you today. And I'm going to give you a context for you to think. So before I do it, are there any questions that you want to ask about the calculations? So let's just summarize what we have done. Okay, let me just summarize because it's been so dynamics.
So you derived this for like this particular equation, right? Like x dot equals minus alpha x plus.
Absolutely, yes, yeah.
But from there, how can you generalize that you can find alpha for any time series?
I have not said it. I know the assumption is that if the assumptions of the model are valid, then I can.
Okay.
Yeah. System near equilibrium. Okay, that's where we started off with. So summary of what we have done today. So we want to understand the dynamics of systems near equilibrium. If we start with any general dynamical system with a noise, then the perturbation around a stable equilibrium follows this OU process, right? And what we have basically shown is the following important result. We have shown that the sigma square of this variable x as a function of time follows this, follows this, this expression, and the correlations or the covariance of this process is given by e power minus alpha t minus t prime. Okay. So this is the main, these are two main results. Okay, and what you have also told me already is that if alpha is small, which means the return rate, low return rate. What does low return rate mean? System doesn't pull back fast enough, right? Sigma square of this x will be large. If alpha is large, means high return rate. If sigma square of the stochastic process will be small. This is what we know. And likewise, you can say something about the correlations, by the way. When alpha is small, what happens to the correlations? When alpha is 0, at least, as a function of alpha, if you were to plot the correlation as a function of alpha, how will that look like? If alpha is increasing, will the value reduce or decrease?
Will decrease.
As alpha increases, the correlations decrease. System is coming back to equilibrium very, very fast, right? That means it's losing that memory. Okay. So, small means low return rate, means high variance. It also means higher correlations. Do you agree with that? And lower correlations. Okay. So this is the summary of what we have learned today. Any questions on this? Okay, so this is the result. Okay, now let me give you the lab work. Okay, so now we know we have studied this model in the previous semester very, very well. And I have also revised this in this, which is basically the logistic model under harvesting. And we know that this model has this feature. And again, this model has come up in the assignment. So this is the stable branch, upper branch, unstable middle branch, the stable lower branch. Okay, and there is a region of bistability. And what this, it has interesting implications. Let's say we have a system which had no harvesting. Okay. Let's say we have n as a function of time. Let's say we had an initial system which is, which is governed by this. Let's also, there's also some stochasticity. Okay, we have added some stochasticity to the model now. And it's fluctuating. Okay, and then because what we will also assume is that the h is increasing with time. Okay, if h is increasing with time, what do you expect to happen? Initially, it's at the carrying capacity. H is slowly increasing with time. Okay, as a function of time, h is increasing, and eventually it crosses a value which is given by this HC2. Let's call this HC1, this value. This is HC2. It has crossed this critical point. Okay. And what do you expect? I think you have done these simulations and we will find something like this. So this is what happens. Okay, as you know, system can now, because of this feature, it can suddenly collapse. I think we had even done an assignment like this in the class, one of the lab works in the previous semester. Okay, does everyone remember this? I mean, I know some of you were not there in the previous class, but does it make sense? Okay, so here is my question for today. You have been given n versus time data. Okay, you have been given this. Okay, and you have been, let's say this event happened at capital time t. T is still less than capital T. That's the data that you have. Okay, up to that you have a T max up to which you have the data, and that is less than the time at which this system collapsed from a high on population density to a low population density. Okay, so the question I am asking you is, can you compute something? Can you relate this time series to OU process? That's the first question. The second question I have is, can you propose to compute some quantities that may help you know that you are approaching HC2. So I want to clarify that you don't know H versus time. That you have not been given. You have not been given H versus time. Therefore, you don't know if you are close enough to HC2 or not. Okay. This is the second question I have. So I have these two questions for you today to think and answer. Okay. So I have the first question sort of acts as a hint, and second question to the second question. So is the question clear to everyone?
So whatever we have derived till now, so we were talking about a single particular stable point, right?
Absolutely, yes.
But here it's like that stable point is also changing with respect to time.
Yes, so the rest of the work is left to you. Yes, I won't answer any further questions. So it is, you're right. So in this case, H is changing with time. Therefore, yeah, so it's not exactly what we have done. Okay. But I'm not asking you to do new calculations, by the way. Okay, just to be clear. Can you still use the results we have derived? And and let me ask, can you propose some, maybe, make any assumptions, make assumptions and state them. Okay. So I'm not expecting any new calculations, by the way. But linking what you have learned and what you know. Is it fine? Okay. So I'll stop here. So I'll let you all go to your breakout rooms. Think about it. Okay. And now one thing I want to clarify and mention is that when you are submitting lab work, only those who are in the group today, only those names must be written in your submission. You must not write your group names of the group members who were absent in the class. Okay. Thank you very much.